Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're continuing with our series on writing a ray tracer in C++ using as far as possible only the standard libraries and the SDL2 library so that we can display results in a window. If you remember back from the previous episode, which was quite a long time ago now, we started looking at implementing multithreading and we got as far as implementing a tile-based rendering system. What I want to do today is to move on to having a look at how we can expand upon that and how we can implement multi-threading so that we're rendering more than just one tile at a time. I just want to say quickly, as I always do before we jump into that if if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Thank you very much. Right, well, without much further ado, let's jump into it and let's see how we can implement multi-threading. Okay, so I'm here at my terminal window. I just want to quickly recap on where we were at the end of the last episode. So if you've been following along, or if you've cloned the repository from GitHub, you should have something like this. And if we go into the QB ray trace directory, you can see these are all of the files that go together to make up the project so far. As I say, if you've been following along, that is roughly what you should have, but do feel free to simply clone the repository and you should get something like that, although after this episode obviously the code will actually be a bit different. Let's just go ahead and run make, if I could type, run make, there we go, to build that. Thank you again to someone for suggesting using the -j switch with make to make it run in parallel. That is much faster. So let's run QBRay, and we can see that that renders in a tile-based fashion. It's rendering each tile individually and one tile at a time. Now actually that's pretty quick to render, but we can go faster because it doesn't take too much logic to see that we don't need to stick to rendering just one tile at a time. We should be able to do quite a lot more than that. If we have a look at the following animation, this shows a little bit about what I mean. So starting with the image that we've got before, let's just rotate that to a slightly different view and divide it up into individual tiles. So this is approximately the situation that we have now. And what we're doing now is rendering each tile individually. So we're picking a tile, rendering it, then picking the next tile, rendering that one, and so on and so on. And as each tile completes the rendering, then it becomes a part of the image, and so slowly over time, as you can see, the image is going to be built up as follows. Now obviously it's clear that we could do something better than this. We have these days pretty much everyone has a multi-core CPU. I've got a 6-core 12-thread CPU, so in theory I should be able to render 12 tiles simultaneously, which is obviously going to make everything a lot quicker, and that's what we're aiming for. Okay, so the situation is, though, you might be tempted to think that why can't we just do a separate thread for every single tile? Okay, one thread for every tile, like so. Well, in theory, yes, we could do that if we actually had that many threads available. That would make sense. If we simply were to dump that out and assume that the operating system could somehow manage all of that, then I think probably the situation we would end up with would not be a lot better than the situation where we're rendering individual tiles. So what we want to do instead is group things together. Okay, so the next thing that we could do would be to, say, render, let's say, 8 tiles at a time, and that would give us a result that would look something like this. Obviously we allocate each tile to a thread, and then we let them render at the same time, and we can see that that would render the whole image a lot more quickly. However, there is a problem with that approach, and that is, as illustrated here, we can't guarantee that every tile is going to take the same time to render as all the others. In fact, we can pretty much guarantee that they won't, unless for some reason they're all the same. So we're going to end up with a situation where some tiles will render much faster than others, and therefore will complete before the others have done. So if we go with the strategy of allocating 8 tiles to 8 threads, and then waiting for them all to finish, we see, as we see here, the number of active threads varies quite considerably. Okay, starting with 8 active threads when we first begin, and then decreasing as the tiles render and as they complete. Now obviously that's not ideal, because that means that we're not getting as much of an efficient result as we can. We're not going to see as big of an improvement as we could get from going for multi-threading. What we want to do instead is detect when a thread is completed and then automatically allocate a new tile to that thread. If we do that, as we see here, we maintain a number of active threads as 8 out of 8 at all times, and we see that this gives the fastest complete rendering of the image. So let's take a look at the changes that I've made to the code to make the first attempt at implementing multi-threading. So we're going to start out in capp.h, which is, of course, as you know, the header file for capp, which is the main class that we have for handling our application. Okay, and we can see that code here. Now we haven't done too much. The first things that we've done are hash include thread and hash include atomic. I'm not going to talk too much about the syntax and everything, really about how these work, because I want to focus on how I've implemented them to make the ray tracing work. But if there's enough demand for it, I could do another episode looking at those in some more detail. But for now, we hash include those into capp.h. We then need to add an additional function here for rendering a tile. Okay, so this is a void render tile. It accepts as input a pointer to a structure of the type tile that we talked about before, and a pointer to the specific tile. We then have a pointer to an instance of STD atomic of type int called thread counter. Thread counter is going to be used to count how many active threads that we have. We need to use STD atomic because this is a variable that can be accessed from within any of the threads. When you spawn multiple threads using STD thread that we're going to be doing, they share memory between them. So variables that are going to be accessed and particularly potentially written to by any thread means that they could be written to in a completely random order. There's no way to guarantee that, and that can create what's known as a race condition, whereby the writing to the particular variable from one thread interferes with the behavior of another thread in an undesirable way. STD atomic effectively allows us to overcome that by essentially providing a kind of gating, if you like, to control how a variable can be accessed. So we're using STD atomic to define any variables that we're going to be accessing and particularly writing to from within our thread code. And we also have another pointer to a tile flag here, also of type STD atomic of type int. Okay. We also have now a new function here called reset tile flags. That's to reset the flags that we've defined there. Okay. And let me see, what else have we done that's new? So we have all our stuff here to handle threads. Up here, though, just to say, this is where we create the atomic. What we actually do is create an STD vector of STD atomics of type ints, a vector of pointers to those called m_tile flags, and that's going to give us a flag for each tile that we can use to represent the status of that tile, to indicate whether it is finished rendering, whether it's currently rendering, or if it hasn't started rendering, or exactly what's going on with that tile. So thinking back to the animation that we've just seen, that will allow us to detect if a tile is just sitting there waiting to be rendered, or if it's already completed, and then we know which tiles that we have left to render. We then have here stuff for our threads. We're defining at the moment int mmax threads as 6, so you set that according to whatever your system is. Okay, you may have 12 threads, as I do. I could use 12, I'm just using 6 for this example. We have an integer variable called m_num current threads that we're using to store how many active threads we currently have. That is, of course, going to default to 0. We then have an STD vector of type ints called m_tiles currently rendering. Okay, so that's a vector of tiles that are currently rendering. We'll talk about that a bit more later. We have STD vector of type STD thread. So we create a vector of threads called m_threads. Okay, that's actually going to store the details of each thread when we create them. And we have finally an additional STD atomic of type int pointer called mthread counter, and that is, as I said, the counter that counts how many threads that we have that are actively running. Okay, and that is everything that we need to change in capp.h. Let's have a look at capp.cpp and see what we need to do there. Okay, so this is capp.cpp. And a few changes we have to make here. Let me just find my, look back in my notes, here we go. Okay, so the first thing that we need to do is in the constructor, the default constructor for CApp, we have to initialize the thread counter here. Okay, so we want to initialize the thread counter to 0. So we do thread counter is equal to new, and I don't really like using the new keyword because it's creating raw pointers, and there could be better ways of using std_thread and std_atomic that perhaps I'm not aware of. I'm very happy for someone to tell me if that's the case, but for now we create a new std_atomic object of type int, which we initialize to a value of 0, and that is our value for m_thread counter. Okay, so the next bit here on init, we need to initialize the thread counter. So we define here m_max threads actually set to 12. That's, like I said, I have 12 threads available in my CPU, so we set that to there. And then what we're going to do is store the value 0 into thread counter. Okay, so we do that. This is of type std_atomic. Okay, so rather than doing m_thread counter equals 0, we have to do something a bit different. So we use the store method from the atomic class, so m_thread counter store 0, and we use the std : memory order release flag with that. So what that simply is going to do is write the value of 0 into thread counter in a thread safe manner. Okay, so guaranteed not to interfere if you're doing operations on this variable for multiple threads simultaneously. Okay, now we have a little bit of change. The next bit is in the, where are we, on render function, I think. Okay, that's all the same. So here, actually on loop, apologies. So in the on loop function, this was the code that we had previously that looped through all of the tiles, find the first one that hasn't been rendered, and then render that tile. What we're doing now is actually quite similar. We loop through every tile that we have. So every time we come through on loop, we are going to loop through all of the tiles that we have available. And for every one, we're going to check the value of tile flags, m_tile flags, that corresponds to that tile. Okay, so m_tile flags.add_I. Okay, so we're going to check if that is equal to 0. Now to do that, because this is an instance of std_atomic, we have to use load and std memory order acquire. Okay, remember that when we wrote the variable using it, we used std memory order release. When we write to it, when we read from it, we use std memory order acquire, okay, like this. So we want to check if the value of m_tile flags at I is equal to 0. If it is, then we know that this tile is waiting to be rendered. So the next thing we're going to do is check if there are any threads available. So we need to check the value of m_thread counter. Again, that's a pointer to an std_atomic instance of std_atomic, okay. So we're going to use load and std : memory order acquire again to check if the value stored in m_thread counter is less than max threads. If it is, then we have a thread available, so we can launch it. In the case that this isn't available, then nothing inside this if statement will get executed, and we'll simply loop through all of the tiles, and that will be it, and we'll then go into on render, and then we'll come back through into on loop again through the next cycle through the main loop of the code, which of course that's sort of how SDL2 apps are apps are designed to work. I have done videos on that before. Anyway, don't want to talk about that too much now. So we have a thread available. Let's assume that m_thread counter has a value that is less than m_max threads. So what we do is we extract the number of active threads, which is the value from m_thread counter, okay, which we do using load and std memory order acquire. We then increment the value by storing into m_thread counter using the store method, num active threads +1 and std memory order release. So we've now incremented the value in m_thread counter. And we then use std_thread. This is the key bit of the code here. This actually spawns the thread. And we're going to call it render thread. That is the name of the thread, okay? And we are creating that with a reference to the function render tile, a pointer to this instance of the class, a reference to the current tile that we want to render, the m_thread counter variable, and the m_tile flags variable corresponding to this tile. And that will actually create the thread which will begin executing immediately. And then we have a choice. If we wanted to simply create a bunch of 12 threads, wait for them all to finish, and then do the next 12, we could use renderThread.join here, okay? But we don't want to do that, because as we saw in the animation, that will lead to a situation that is not as efficient as we really want. So what we do instead is we use renderThread.detach, and what that does do is that releases execution back to everything, so we can just carry on. This thread will now just carry on and will terminate and delete itself once it's finished. Of course, because of that, it has to make sure to store its results somewhere. We'll come to that in a moment. But this is the most efficient way. So once this thread is created, it begins executing immediately. We detach it, and then we can simply go back to looping through this loop again. We check if there are any another tile that needs rendering, and if we have a thread available, then we would go ahead and render that. Okay, so we also make some changes to the onRender method. The onRender function, just a little bit down here. This is the code that we had previously. If m_tileflags.i is equal to 2, then we take care of actually rendering it to the screen. So we're using the value of 2 to indicate that the tile is complete and therefore ready to be rendered. So just to recap a little bit, every time we come through the onRender function as part of the main loop, we are going to be generating the display, and we want to be able to see the display as we're going along. Okay, we covered all of that in much more detail in the previous episode. So what we do now, we simply replace that line with if m_tileflags.i is equal to 2, but we do that now using the load function from the SDD_atomic class. Using std : memory order acquire, as we've already seen. So that will check that the value, if the value of m_tileflags for this tile is equal to 2, and if it is, then we go into this code here to actually do the rendering. Again, we covered that in the previous episode, so I'm not going to talk about that here. That's all the same. The next bit that's changed, let's see. Okay. So the next bit that we have is this function here that's responsible for actually rendering a tile, and this is the function that gets called when we spawn the thread. So it is essentially the code that runs in each thread. It accepts as input a pointer to the tile object, a pointer to an SDD_atomic for the thread counter, and a pointer to an SDD_atomic for the tile flag. We modify the value of tile flag to 1 using the method that we've seen before. Okay, to what value of 1 to indicate that this tile is currently rendering, and then we call the render tile function from the scene class, passing a pointer to the tile, okay, to actually perform the rendering. We've seen that before. What we're going to do after that is decrement the number of active threads. So once that's finished, we come to here, we create an integer called numActiveThreads to the value of thread counter, and then we store into thread counter numActiveThreads -1, okay, because we've now finished that this thread is no longer active. And finally, we modify the value of tile flag to the value of 2. Okay, so you can see where this is a pointer to a particular tile flag in the array of tile flags, and we're modifying it everywhere here in the thread, and you can see that other threads are going to be looking at that particular tile flag at the same time, which is why it's really important that we use the SDD_atomic to avoid the possibility of race conditions. And finally, we have the function here, reset tile flags. All of this does is simply what you'd expect from the name. It simply modifies the tile flags by storing a value of 0 everywhere using the store function from the SDD_atomic class, and it modifies the texture complete variable to false to indicate that the texture is no longer complete for that class. Okay, and we talked about that in the previous episode. Okay, so that's pretty much everything actually that we have to do to implement multi-threading. Okay, the only last place that we need to look to make a change is in our make file. So if you remember right back to the beginning of the project, we're using gmake, or I'm using gmake. If you're using some other system, some other build system from Visual Studio or something like that, then you will just probably need to find a way to modify the flags that we're passing. So we know we're passing that we want to use C++17, we're using -o fast, we get the fastest possible compiled code. What we need to add is -pthread, just to tell the compiler that we're going to be using multi-threading. Okay, and that is actually everything that we need to do. If we compile that code now and run it, we should have a very basic implementation of multi-threading. So let's have a look at that now. Okay, so just in the terminal window, we've got all our files there. I'm just going to run make. Let's compile our code. Shouldn't have made any errors because I did write this code before. So let's just, there we go, let that finish, and now let's run QBRay. And well, there you go, that completed quicker than I was able to drag it across onto the monitor where I'm doing my screencasting, so that's good. Very clearly we had multi-threading. Let me just try that again, see if I can bring that over faster. It's too quick. Okay, so that's good, right? We've achieved what we set out to achieve. It's now fully multi-rendered. It renders in less than 1 second, really, or just maybe about 1 second that it takes me, and that's quicker than I can coordinate myself with the mouse to swipe the window over. So good, we're done, apart from the fact that it doesn't look right, does it? Very clearly there's a lot of weird stuff going on here, and the reason for that is actually because we've created some race conditions, and before we can properly do multi-threading we need to address that, because there are some areas in the code where we have not created code that is thread safe. So what's happening in some parts of the code, we are storing values, like for the surface UV coordinates, for example, are actually stored in the class instance where they're calculated and then retrieved where they're needed by other code. And the problem with that is, of course, you're going to be calling the same object from multiple threads simultaneously, which means those UV coordinates are going to be varying randomly depending just on whatever, threads are currently active on the same object. So that's clearly no good. Okay, so the next thing that we need to do, we just need to look through our code and we need to modify it to make sure that we don't store any UV coordinates in the actual object class instances. So let's have a look at that now. Okay, so what can we do about this? Now, we mentioned before that we have to be very careful to avoid race conditions, and previously when we've looked at code that has to be accessed from multiple threads simultaneously, we use the SDD atomic class to help us to do that. Now, we don't need to do anything like that in this occasion, but what we do need to do is make sure that we're not storing any data that we later use in each instance of an object. So what's happening here particularly is that we're storing the UV coordinates in the object when we test for an intersection, and then we're retrieving those UV coordinates later on to use them to evaluate the texture or surface normals or anything like that. Now that causes a problem because multiple threads will be accessing the object instance at the same time, and they will, of course, be testing for intersections at different places and will therefore be generating different UV coordinates. So what's happening is that the different threads are writing or storing different UV coordinates in the object instance, and then when any particular thread happens to come along to retrieve those UV coordinates, it's pretty much random as to exactly which UV coordinates it's going to get. And that's the reason we get the broken up image that we just saw. So what can we actually do about that? Well, to fix it, we need to make sure that we don't store the UV coordinates, or anything else for that matter, in each object class instance. So we're going to have to make some changes to the code, and actually we're going to start in the material classes because we're going to make some changes to those so that we can pass the UV coordinates to them, whereas previously they simply retrieved the UV coordinates from the object instance. So let's have a look at that now. Let's start with materialbase.hpp. Okay, so this is materialbase.hpp. So this is the base class for all of our materials, and the only change that we've made here is in the compute color function. which is responsible for computing the color for this material at a given point, is that we've added two new variables that are passed into this, corresponding to the local POI, the point of intersection, which is a QB vector 3, and also the UV coordinates, okay, which is QB vector 2. So UV coordinates simply a two-dimensional vector, okay, and that is the only change that we need to make here in the header file. Let's have a look at materialbase.hpp. Sorry, of course I meant materialbase.cpp. Here we are. So materialbase.cpp, again, we've simply added this line here to the compute color function inside the function declaration, so that we now have the inputs for local POI and UV coordinates. Now we don't do anything here in the base class, so we don't need to make any further changes. So any further changes we make now are in the implementations of those. So let's have a look at simple material.hpp. Okay, here we are, simple material.hpp, and now this overrides the compute color method or function, right? So we obviously need to make the same change here. So we put in QB vector 3 local POI and QB vector 2 UV coordinates. Okay, the only change there. So let's have a look at the CPP file where there's actually some more substantial changes. Okay, so this is simple material.cpp. And let's have a look. So obviously we modify our version of the compute color function that we're overriding from the base class, and of course we add QB vector 3 local POI and QB vector 2 UV coordinates here. And what we're going to do, so this is the example of what I mean of what we're having to change. So previously we calculated our new normal by perturbing the normal according to the normal map, for example, in the case that there is a normal map. And we retrieved the UV coordinates directly from the object that we're dealing with, the object that this material has been applied to. Now this is what we can't be doing in a multi-threaded environment because of, as I just explained, multiple threads can be accessing these UV coordinates at the same time, and they could be writing to those, and so when we come to retrieve them, we're essentially getting completely random UV coordinates. There's no guarantees about what they're going to be. So we need to do something different, and what we're doing now is we're having the UV coordinates passed to the compute color function as a variable, and then we simply refer to that here. So we simply modify this to new normal is equal to perturb normal, new normal, UV coords passed from here, and the up vector as before. Okay, and then we go through and we simply make similar changes everywhere else where we need to get the UV coordinates. So here, for example, where we retrieve the texture color, we use the get texture color function, and we simply pass the UV coordinates, whereas again before we were retrieving those directly from the object instance, and so on. And that's basically it, I think, for simple material. Okay, now we have to do exactly the same for our other material classes. Okay, so this is simple refractive.hpp, exactly the same. We change our overrided version of the compute color function. Okay, and simple refractive.cpp, again the same. We put in local POI and UV coordinates as input to the compute color function, and then just as before, everywhere where we were accessing the UV coordinates directly from current object, we replace that to the UV coordinates that we're passing to it. Okay, and that's basically it for the basic material classes. Once we've made those changes to the material base class and the actual implementations of the materials, we need to make some changes to all of the object class files. Now I'm just going to show just one example, and the changes are similar across all of them. So I'm going to show for objectsphere.cpp, we only need to change the CPP files, and if we just come into the test intersection function of each one, come down to the end where we actually calculate things. So previously we were storing the UV coordinates and in the m_UV coords variable and retrieving, and we did pass that into hit data as well. What we want to do now, instead of storing it in m_UV coords, we simply pass it directly. So we use the compute UV function that we now have. Yes, and in fact that we had before, sorry, with the point of intersection, and we simply pass hit data.uv coords directly, and that's a reference, I believe, to hit data. It should be, yeah. So what that will do is simply then compute the UV coordinates and store them directly into this hit data variable that then gets returned here directly from the test intersection function. So we're no longer storing anything in our class instance, okay? And that is really what makes the difference, okay? Okay, so one last change that we need to make that I forgot to mention. If we look back in material-base.cpp and come down to where we have not compute color, compute diffuse color, for example, we don't need to change that one. No, that one's okay. Compute reflection color. So compute reflection color has a call here if our object has a material. Okay, our closest hit data, because we're casting another ray, then we need to change our call to the compute color function so that we pass now local POI and the UV coordinates. And we need to do that everywhere else where we will interrogate a material, okay, to make sure to find its color. The other example is in the scene class, so let's just have a look at that. Okay, so if we look in scene.cpp, and we need to come down to not cast ray, I think that's all stays as it is, yes, render pixel, we want to look here, so this tests if the object that we've hit has a material, and if it does, it calls the compute color function here, and so we just need to make sure that we pass specifically closest hit data.local POI and closest hit data.UV coords, okay, so that will be responsible then for passing the UV coordinates to the material so that it can then use those to calculate the color. And that saves us having to actually store anything, which is exactly what we want. So let's compile that with those changes, and let's have a look what result we get now. Okay, so back at my terminal window, let's just run make, compile everything. It shouldn't take too long. Okay, that's good, and let's run QBRay and let's see what we get. And there we go. So you can see that that is now immensely fast because we're properly multi-threading, and all the texture mapping and everything now works exactly as it should. Okay, so that's really everything that I wanted to talk about today, and that pretty much wraps up what I want to talk about to do with implementing multi-threading. Now, I know some people have questioned using multi-threading with SDL2 because of the overheads that SDL2 apparently imposes. I personally have not found that to be a problem. I mean, everything here seems to work. Now, it is possible that we're not really being as efficient as we possibly could, and if we were trying to create a real-time ray tracer with frame buffering and everything else to make real-time animations, then we probably would want to do things differently. But it's never been my intention with QBRay that it should operate in real time, especially when we come to start looking at path tracing. I've posted some pictures and the results from that. It's impressive, but it's very slow. So real time is really not what we're aiming for, and therefore some inefficiencies involved with setting up SDL2 to create the window display that we have and all that sort of thing, I don't think really matter, as long as what we're doing when we actually render the display or actually ray trace the images as fast as possible, then I kind of think that's really what we need to be aiming for. Anyway, I won't ramble on too much, so listen, I really look forward to seeing you in the next video. Thank you very much for watching. Bye.